presentation, we would like to understand a little bit about data warehouses. Have already seen that data warehouses collect data from a variety of disparate resources. They aggregate data or collect data from different operational data stores. The operational data stores being those data stores that run the business. And we were already seeing that the data warehouse forms the basis from which multidimensional databases are created. So that the data warehouse in many organizations forms the code, single version of the truth for the organization. It's the repository for all data that has been cleaned and verified. And so it forms the basis for a very accurate data source for the entire organization. And the data warehouse then becomes a key player in different types of BI solutions that exist. We are going to be looking at reporting solutions from a data warehouse directly from multi-dimensional cubes and going to look at OLAP applications. In any case, it's necessary for us to understand the structure of the data warehouse so that we know how the data in multidimensional databases organized and so that we can accurately report information. Information systems for an organization can be divided into two major categories. Operational. That is those systems where the data is collected, those systems that organization needs to function. Basic accounting systems, basic inventory systems, and then the analytical systems, that is where we are focusing in the course, where the data is analyzed, the focus of business intelligence. And those systems, while perhaps not necessary for the organization to accurately function, are in today's information world necessary for the organizations to function well. The data warehouse then is the main repository for these analytical systems, and it is, as we mentioned, the foundation for business intelligence and that types of systems that we will be discussing in this course. A good data warehouse has the following features. It's very easy for the organization to access the information in the data warehouse. It provides that single version of the truth. Consistent, accurate information across the organization, across all departments, across all divisions. A good data warehouse resilient to change. They can also be hard to implement, but they are good structures for data warehouse design. Security, another big issue in today's world, and another thing that requires high degree of attention and detail. So it is also really important, the final bullet, to say that to find that the business users use the data warehouse that is well accepted. That is, it's trusted and a good technology solution isn't efficient. It's necessary for the business user to be involved and in the design of data warehouse and they finally have their acceptance. Acceptance attesting their design of those sign approval that data is accurate. The data warehouse structure is what we are looking at today, and we are going to contract it with a typical relational database structure that is highly normalized. The data warehouse itself does sit in a relational database world, so it's very much like operational systems in that respect. And some data warehouses can be normalized structures, the structures that are used in operational systems. If this is the case, then generally the data warehouse is used to populate other data marts of a dimensional structure. So we are going to discussing then the data dimensional structure here, and what that is what we sometimes refers to as the star schema. If you remember the first slide, it says reach to for the stars. So the structure, the way the tables are organized, and the way the relationships developed among the table is different here for data warehouse. The whole reason for that is we can facilitate analysis and reporting. So what is dimensional structure? First, let's consider the normalized structure have a typical operational database. Here's a small example. We're interested in collecting data orders for widget. Let's see that's And we design our tables in the following manner. We have an order table to collect what we would call the master information for the order. That information that doesn't pertain to each item ordered, that rather pertains to order as a whole. And then we have the order detail table that contains the information for each item, each widget that might be purchased, the quantity, the unit price, and so on. But we make sure that we don't duplicate customer information or order date on each detail line. We collect that only once in the orders table, and then we have related to our order a customer. And that relationship takes place using the customer ID number or customer ID code. And again, we don't repeat the customer's name, the customer's address on each row in the orders table. We simply refer to that information, the name, etc., about the customer using the customer ID. So our operational database, our normalized structure reduces any replication of data, which is of course very good if you're entering data, because if we have to change it, we don't want to change it in more than one place. The dimensional structure, however, is not focused on data collection, but rather on analysis of data. And we often organize this structure in what's known as a star schema. In the center of the star, we might have a fact table. We might have facts, measures, numbers about daily sales. This would be where perhaps information from the order and order details table might be collected. And then we have various dimension tables. One for the customer information, one for the product, one for the date, and one for the store. This is just an example, but the structure, a fact table central to a number of dimensional tables, is typical of star schema and dimensional structure. The fact table are primary table, kind of center of the star where numerical performance measures are stored. This might be cost measures, quantity measures, and other types of numbers. And the row in fact table really responds to a measurement, might correspond to the sale of one item, it might correspond to an inventory reduction, and the fact table generally have many rows. Dimension tables, on the other hand, don't typically contain numbers per se or measures, but rather they contain the descriptors of the measures. What information? How is the business interested in analyzing that information? There are generally many columns in a dimensional structure and typically possibly not so many rows in the fact table. This is the customer business or interested in analyzing sales by customer. They're interested in analyzing sales by store. They're interested in analyze sales by fiscal year. So the dimension is that helps us to implement analytical slicing and dicing. So to some of the data warehouse, it's the question why the word dimension sometimes come up. And I would say it's because people tended to visualize these types of problems in terms of dimensions, in terms of looking at a cube. Sometimes we call a dimensional database a cube. So in these particular examples, customer values might lie along one dimension, product values might along another, and time along another, and the facts might be the little intermediate cubes that are formed by intersection of product, customer, and time values.